presentation, accuracy of model concrete in square and rectangular column confined with the FRP with different failure strain proposal presented by Mariana. Jesus.
Boa tarde a todos, good afternoon to all. I'm Mariana. Today I'm going to present the accuracy of models of confined concrete in rectangular columns using different proposals for the prediction of the failure of the FRP. Confinement with external application of fiber-reinforced polymers FRPs improves utility and strength of concrete elements. For this reason, this has been a more common solution in our days, using carbon, using glass or aramid FRPs. The prediction of the stress-strain relationship of columns confined with FRP under monotonic load was presented in several constitutive models. However, few models can be applied to square and rectangular cross-section column, and even fewer can have good results by predicting the strain of the FRP. The constitutive models for FRP can be divided into main categories: theoretical models built around physical concepts, and design-oriented models built around the experimental evidence and the calibration of some parameters. Here we can see the models that we use in this study. So we use only design-oriented models. This was from the model by Faustino et al., Jesus et al., Lamenteng, Manfredi and Helfons, and Wei Wu. But these models cannot be applied blindly to the concrete columns. We have to take into account the geometries and the types of FRPs that we are using. For example, in this case, all these models can be applied to columns with square cross-sections, but only the model by Lamenteng and the model by Wei Wu can be applied to rectangular cross-sections. Regarding the type of FRP, we can see that the models by Lamenteng, Helfons, and Wei Wu can be applied to all types of FRPs in the study, the glass, the carbon, and the aramid. But in the model by Jesus et al. Can be applied only for square columns confined with GFRPs, and the model by Faustino et al. Can be applied only to carbon FRPs. To the accuracy of these models, we need experimental tests. These tests were found in literature. And what type of tests we were looking for? The ones with full information about geometry, about FRP properties, and about concrete properties. Regarding the geometry, we have B and H as the small and the larger size of the columns, and R the corner radius. Regarding the FRP properties, we consider the tests with the information about number of layers, the design thickness, the youngest models of the FRP, the ultimate strain provided by the manufacturer, and the observed value, the observed strain value from the experimental test. Regarding the concrete properties, we have researched ones with information about the unconfined concrete strain and the respective strain value, and the maximum concrete strength and its axial strength. Comparison of numerical experimental results. The accuracy of these models were assessed with different proposals for the prediction of the failure. The study was divided according to the type of FRP and geometry. This is really divided in square columns confined with CFRP, with rectangular columns confined with CFRP, square columns confined with GFRP, and square columns confined with AFRP. So, due to the lack of experimental tests, it was not possible to study rectangular columns with confined with glass and confined with aramid. In glass, there was only found one test with all the information that we need, and there is in the aramid there was no one with all the information that we need. That is actually a problem that we are finding and when we're working with this type of experimental tests. So then the comparison between the numerical models and the experimental tests were done, and we focus on the analysis of the error of the parameters, and these parameters were the strength, the maximum axial strength, and the strain energy density. Here we can see the equations that was used to couple the models. We can see we work with the ratio between the observed strain failure and the ultimate strain provided by the manufacturer. We can see that in some cases, as is the case of over here, Ilki et al., Lamontagne, and Tutangi et al., we only have a reduction made by a simple constant. In other cases, as is the case of Lima and Osbach-Lobo, we have this reduction of the ultimate strain takes into account the Young's model of the FRP and the unconfined concrete strength. In the other cases, they are influenced by a geometric parameter. This is 2 times r divided by b, so it's, you can see over here, for example, so small. And this geometric parameter it's used for about 20 years, maybe, or a little more. Okay. There are some variations. For example, in Mafrenic Alfonso, it's not times 2; it's only r divided by b. And we take into account again, like in the models, the geometry and the type of FRP. So we cannot apply these equations to all models that we have. So here we have the error. We work with the error in percentage. We have the error that we found for, in this case, for carbon. We have all the equations that are applied to square columns confined with carbon, and the models that will be applied to this case. These are the percentage of error compared to the values of the experimental test. And here we have, from these values, what have we done? We see, for example, in this situation, for the model by Faustino et al., we look for the small error for each parameter. This is the small error for the maximum strength and the small error for the axial strength. And with this, we come to this graphics where we can see the experimental tests and the models coupled with the equations that presents the the small values of error. We can see, for example, in specium KR2C2, for example, is this specium over here and this graphic over here. We can see that the experimental test is very different from the models coupled with these equations. And that can be seen, for example, when we see the strain energy density. Okay, what is this? This is the area over here for between the stress and the strain. Okay, it's the area of the graphic, and we can see that we have high values. For example, some are about 60% error regarding the strain energy density. And when we look at the value for the rupture of the fiber, you can see that in equation 3 we have the smallest value, about 30.3% of error. Repeating this for the other cases, for example, for rectangular cross-section confined with FRP, we have less models that could be applied over here and less equations as well. And these results are a little more nice. We can see that, for example, in these two, visually, it's not even necessary to look at the value itself. You can see that this one over here is not, no model can predict the response. The models that could predict the stress is not able to predict the strain. That happens here as well. And not following totally the behavior of the experimental test, but with similar stress and strain values. You have these two over here that have some more accurate values. Looking at the table, we can see that these errors are about 0.29, for example, for the strain energy density, and the prediction of the failure about, for example, over here, Way and Wu coupled with equation 5, we can see an error of 0.64. Then button something should be broken. So for the square columns with GFRP, repeating the process, I can see here how, the comparison between the experimental test and the models coupled with the equations. You can see that with the exception of the second one over here, that we have some models that are more close to the experimental response. In the other case, we have very different behaviors, and that could be seen here in the table, where you can find errors of, for example, 400% of error. That's a lot. 400, 700. That totally is not in agreement with the experimental test. For square columns confined with the FRP, we can see that only the experimental test AS could be predicted by our models coupled with almost of the equations, but when we see these trees over here, you can see that they have a very distinct behavior. So, for main conclusions, the models by Manfredi Helfons coupled with equations 3 and 5 present the most accurate stress-strain response for square columns confined with CFRP, and the remaining models could predict some of the parameters, but graphically we don't see that happens. Regarding column with rectangular cross-section confined with CFRP, the model by Wei Wu coupled with equations 5 and 8 delivered the most accurate stress axial strain response in comparison with the experimental test, and in two of these species, the models were not capable to satisfactorily predict the stress axial strain curve. The model by Wei Wu coupled with equation 5 is the most adequate for square cross sections confined with the FRP, and in 3 of the species the values were not good enough, where the model was not sufficient. For columns with square cross section confined with AFRP, only the specimen AS shows good results, accurate results, and for the other species, high values of error were found. Therefore, the models coupled with the equations that we found were not didn't provide good results. The use of different proposals in the existing models allow to obtain better stress axis strain compared just testing the model without these equations. And the use of equations 5, 7, and 8 allow to improve the response of the models in 60% of the cases, while the use of equation 4 allows better results in 50%.
Question from the floor?
Could you go back to the previous slide? You mentioned use of different proposals. Could you further clarify what do you mean by different proposals?
So, these different proposals are the equations that are these equations that is
So you change
yes, so,
constitutive equation.
exactly. So we have the model, and some models it can predict the failure of the FRP, but they used sometimes they use the manufacturer value, and this has been seen in literature and in experimental tests that our group has made.
So you change the constant of the constitutive equation.
If it's a constant, yes. So
And this
the
is done by
main point.
curve fitting procedure.
Sorry.
How it is done in practice.
So in practice, we programmed the model, and we changed the way of getting the failure strain of the FRP. For example, some of the models use the value given by the manufacturer, but in most of the experimental tests that we have performed and found in literature, that value is it's small. It's much more small, sometimes 50–60% smaller than the value provided by the manufacturer. There, some researchers try to find equations or constant, just a constant that could tell us what should be the constant that we have to apply to the value of the manufacturer. So we are in we can take advantage of our FRP.
Thank you.
Okay. Okay, fine.